first guest talk. So we're very pleased to have Nicolas Pajerno. He's currently at Google Brain, but he recently finished his PhD at Penn, where he did a lot of the early work sort of laying out many of the challenges for machine learning and security. And he'll, after being at Brain, be joining the faculty at University of Toronto. And today he's going to give us an overview of many of the topics in security and privacy and machine learning. Thanks, Jacob. Thanks. Can everyone hear me well? So people should feel very free to ask questions.
Yeah, that's what I was going to say.
And we'll also have 20 minutes at the end for sort of more focused discussion.
Yep. So yeah, so the goal of this lecture is really to help you identify open research problems at the intersection of security, privacy, and machine learning. My understanding is that you'll have other lectures afterwards in the semester with more speakers covering some of the topics that I'll discuss today in more details. So the way that I'd like to go over the research that we've been doing at this space is basically by drawing comparisons with more traditional computer security. And I hope that you'll find it useful in this way to basically identify what remains to be worked on. A lot of the ideas that I'll be discussing today, I wrote them up in a technical report that has the same title than this presentation. So if you miss any of the ideas or you're looking just for more references to read, feel free to just look up the report or to ask any questions during the presentation. So to get started, I'd like to take a really simple example to understand some of the limitations of machine learning. So here, let's even assume that we don't have any adversaries in the picture. And let's consider the example of a medical insurance provider that would like to decide whether to provide a policy to a specific individual. So you can see how machine learning can be useful to do this. You could build a model that takes medical records and tries to predict whether the individual has a high risk of having things like cancer or diabetes, or is just a low-risk individual. And based on that, you could decide whether to provide them with insurance or not. By doing that, and in order to be able to train the resulting model, we are making an underlying assumption that the training and the test distributions are going to be identical. And this allows us to use a lot of the tools and techniques that have been designed in machine learning, such as, for instance, the cross-entropy loss, where we'll try to gradually push the model's predictions towards the labels on the training inputs that we're analyzing. So this generally works fairly well, and we can obtain, as we know, very accurate models in many application domains. But there are a lot of corner cases that we should consider. And so one very simple example in this particular setting could be an outlier patient that you haven't captured in the training data. So for instance, if you have a patient that is nearsighted and you haven't taken that into account in the training data, then the model that you've trained, even though it may have performed very well in all these other individuals, it will be basically useless in this particular setting, and you cannot rely on its predictions to make any decisions. And so here you can see how in the real world, assumptions like the fact that the training and the test distributions are identical may not always hold. And so obviously this is going to get even worse as we introduce an adversary in the picture. So now, let's take the exact same example, but consider someone that is actively trying to evade the system that you've created. So the adversary could be motivated by, for instance, paying less insurance. So they could try to modify the medical records before they submit them to your model in order to force your model to decrease the risk of the patient and maybe provide a policy that is cheaper. So we know with things like adversarial examples that for the very reason that it's easy to train machine learning models, and in particular the architectures that we work with today, it's also very easy to find perturbations of their inputs that will force the models to make wrong predictions. And the reason is that it's easy to backpropagate the error of the model through the gradients back to the model parameters. And for that same reason, you can backpropagate the error all the way back to the input and find perturbations that will push the model's prediction towards what is of interest to the adversary. So here, if you think about adversarial examples in this context, it's clear that they could be used to target our model. Yes?
So I sometimes see similar considerations used to motivate sort of like incentive compatible learning models, where instead of thinking of people as adversaries, we just think of them as selfish agents that have their own incentives, and then we try to incentivize them to do the right thing. So I guess I'm curious when you think one or the other of these models is sort of like the right way to think about things, the more economic versus the more security worst case model.
I guess it always depends on what the motivations are of the adversaries and where their incentives come from. And the model that you're suggesting might work when the incentives are just a little framed differently, if that makes sense. Yes?
I don't quite understand what perturb means. So we can't fake the medical record in this case, right? So how small of a change are we talking about?
So I guess, yeah, I sort of didn't describe that into details, but basically you could assume that a malicious individual would report wrong medical records as you submit. This is an example. I'm not saying it's possible in practice, but this is just, you could imagine someone reporting wrong. Just as you fill your medical records, you could just report the wrong information. Any other questions? Okay. So another way that the model could be targeted is basically if the adversary is interested in the training data that the model has analyzed during training. So a lot of the machine learning is applied to sensitive training sets. So in this case, in healthcare, it's very obvious that you're analyzing patients' medical records. And so you can see how having access to some of the information encoded in the training data could be valuable to the adversary. And so we've seen things like membership inference attacks, where the adversaries use access to the model's predictions to basically infer whether a particular point was used to train the model. And so this can be a violation of privacy. For instance, if you think about a model that is used to detect a specific medical condition, being part of the training set can be very sensitive and very private information. So that's just one example. We've also seen attacks where adversaries will gradually extract the model parameters and basically the model decision boundaries through a prediction interface. And so here again, you're coming up with the risk that being able to analyze these individual parameters might reveal information about the training data. So in short, this really reminds me of a law that economist Goodhart stated a while back, which is that when a measure becomes a target, it ceases to be a good measure. And so as we are applying machine learning, not anymore to things like translation, but to things like malware detection, modeling financial data, or just healthcare, as we just described, it's clear that the adversaries will have incentives to have the model misbehave. And so we've seen things like using adversarial examples to evade malware detection. So that makes a lot of sense because you can craft at scale many variants of your malware that will go through the filters. Modeling financial data, the incentives are very obvious for the adversaries, and healthcare I just described in details. So now in this lecture, I'd like you to think about this question, which is whether machine learning is any different from traditional computer security. So in traditional computer security, we usually have something that looks like an arms race, where adversaries will identify a vulnerability in the system, and the defenders will patch it. And then you'd keep going with this arms race. And this is one of the reasons why in 2004, Butler and Lamson made a comparison between traditional computer security and real-world security. And in both cases, what you're really doing is you're balancing the cost of protecting with the risk of the loss. So in the real world, it's still very easy to break into people's houses. We have things like locks, which are defenses, and they may prevent very inexperienced adversaries from breaking into our homes, but they will not prevent someone that has a lot more incentives to break into your house from breaking it. And so in computer security, that's sort of this balance that we've been looking for, trying to design mechanisms that are not too expensive so that we can actually deploy them, but that are appropriate for the level of risk that we're facing. And so the question that I'd like to think, that I'd like you to think about really is whether machine learning offers a paradigm that is sufficiently different that we don't have to think in this way, so in this arms race way, but rather that we can approach security and privacy in a principled way. And so my hypothesis is that this is true, that we should be able to approach security and privacy in a principled way in the context of machine learning. And the whole reason for this talk is to basically motivate why that is the case. And let me give you a very short example to get started. So it's basically a comparison with cryptography. So if you look at the field of crypto, the real crypto, if you look at a couple of years in the past, there was not much progress that was made in the community, right? Until the game between adversaries and defenders was formally defined, and we modeled what are the adversarial capabilities and the adversary's goals. And then we went from protocols like SSL, which are in some way a best guess effort, to TLS 1.3, which brings hard mathematical reasoning to prove the security of the protocol. And if you think about it, a lot of these crypto systems are expressed mathematically in large parts. And machine learning is also made up of components that are expressed mathematically in large parts. So I would argue that machine learning may be more amenable to formal specification in the context of security and privacy for this reason. So I'm not proving this statement. I'm just putting it out here. And the reason for this talk is to sort of make you think about this. And I definitely encourage you to explore this in research. Yes?
So are you contrasting this, when you say more amenable, this is like in contrast to physical locks and keys, or to like web security, or to cryptography?
Yeah, to things like web security or operating systems security.
So I'm confused because I think of SSL and TLS as instances of web security, but you seem to be pretty, like using those as examples of more secure.
I guess I mean the underlying protocols for these mechanisms.
Okay, so,
so
you're
basically
saying like TLS, like SSL, or sorry, TLS is like secure, but maybe like I don't know, like random website on the internet that takes your credit card data may or may not be secure.
Right. It's just that basically, if you look at the proofs behind these, the quality of the mathematical reasoning has improved a lot, and based on that, you have guarantees that are much more robust as the time goes on. Okay. So having made this comparison, it's really natural to look at machine learning security and privacy through the lens of Seltzer and Schroeder's principles. So these principles were enunciated in 1975 in the context of crypto as desirable properties, desirable characteristics of protocols. And when preparing for this talk, I was really surprised how many of these principles are very relevant to what we've been doing in machine learning security and privacy. And so in the report that I mentioned in the title slide, I go over all of these principles and give examples of how they relate to machine learning security and privacy. Here, I'm going to focus on 5 of them and walk over some examples, some specific examples of why I think they really matter to the problems we're thinking about. And then from there, I'll move on to basically 2 research directions, which I think the community has not addressed sufficiently, and which would have a lot of value if we could make progress. So let's start with fail-safe defaults. Here, the principle is that you want to base security on permission rather than omission. And so there are multiple ways that you can think of how we could implement this in machine learning. So for instance, a very simple example is if you're deploying a machine learning model, you might choose to not reveal its predictions when it has low confidence at test time. So that's a very simple mechanism. It will not solve all of your security problems, but it will slightly push the adversary's boundary for success. You can also think about implementing this principle at training time. So if you're trying to train a model in an online fashion where you get batches of data over time, and then you would gradually apply these batches of data to compute model updates and refine your model as it's being deployed, you can see how this would be vulnerable to poisoning, right? As the adversary knows that you're learning in an online fashion, they could gradually insert poison into your training data to force you to extract corrupted logic. So you could see how Defender, rather than systematically applying the data that it receives to compute model updates, would instead compute a candidate model every time it receives enough data and compare the performance of this model to all of the previous models on a holdout data set. So this would allow the adversary to compare the performance of the models and perhaps identify if something suspicious is going on, because the performance, for instance, drop would be more than a certain threshold. So this is not going to solve all types of poisoning attacks, but it will force the adversary to gradually insert the poison rather than being able to corrupt the logic in one single batch of data. You had one question, yes?
I think I was just going to ask about like the threat model here. So it's like the adversary, it's like the attacker. Do they like see our model's predictions at test time? Is that why we don't want to output them?
Yeah, so well, I guess here the idea, you mean the first example?
The first example, yeah.
So the first example, the idea is that sometimes it may be better to not make a prediction rather than making a poor prediction, an incorrect prediction. So that's just, it's a very simple concept. I'm not arguing it would defend against very elaborate attacks.
Would be a good example.
Exactly, yes. Because if you cannot recognize the person with enough confidence, then you just decline identifying this individual. Yeah. So yeah, so that's another simple instantiation of this principle. So the second principle that I wanted to go over is the one of the open design. So here, the idea is that the security of the system should not depend on secrecy. So this is basically why in crypto the security depends on the key and not the particular protocol that people are following. And this is extremely relevant to machine learning security. We've seen many instances of this, in particular in work on adversarial examples, where it has essentially occurred that black box attacks are not much more difficult than white box attacks. So there are many reasons for that. The first one, the most simple one, is that the black box model might become a white box after, for instance, you have an insider that would leak the model, or you could imagine that you're deploying this model on user devices or in software, and the adversary might use something like reverse engineering to extract the model parameters. But even if the model was to remain a black box, we've basically seen that it's fairly easy for adversaries to extract models that are sitting behind prediction APIs. So as long as the adversary is able to select queries and observe the prediction of the model, they can basically select these queries so that they efficiently learn enough about the decision boundaries of the black box model that they can replicate it locally. So what happens is that the adversary is going to gradually interact with the prediction API to poke around the decision boundaries and then extract enough information that it can replicate a copy of the model locally on the machine. And so this local copy has complete white box access. The adversary can access it. And so what you see here is that this is extremely useful to then mount other attacks. So I mentioned the use case of privacy previously, so the adversary could try and extract information from this model, but they can also use it as a way to find things like adversarial examples. So what we found is that essentially if you have this local copy, you can use the white box attacks on the local copy. So you can use things like gradient-based search heuristics to walk on the decision surface and find inputs that your local model will misclassify. And then you can transfer them back to the black box model. And so the black box model will also misclassify these inputs. So the reason for this is basically called transferability. There is no clear explanation yet as to why transferability holds, so why different models make the same mistakes on these adversarial examples. But you can think about a couple intuitive reasons. For instance, the fact that we have machine learning models with very large error spaces means that if you take two models, the intersection of their error spaces remains fairly large. And so it's very likely if your attack finds an input that lies in the error space of one model, that it also lies in the error space of the second model. So this has basically led to the conclusion so far that you should not assume that a model that is sitting behind some form of prediction API, so that is a black box, is any more secure than a white box model that the adversary would have direct access to. Yes?
In this example of transferring attacks that fool one model to another model, is that in the explanation of this case, does that assume that the attacker has access to the same training set that the defender used?
Yeah, so that's an excellent question. So basically, what happens is that if the adversary has access to the same training set, it makes their job easier. And the reason is that they basically have very good queries to make to the black box model. If they don't have access to the training set, then essentially what happens is they need to synthesize the queries. And so it may increase the number of queries that they have to make before they extract enough information from the black box model. But we've seen cases where with like vision models, if you start with just a handful of examples per class, then you can, based on the feedback you get from the model, you can construct new inputs that you query to the model completely synthetically without having access to any real form of training data. Okay. And so just to give a little bit more details on this open design principle and how it relates to black box attacks, I want to give you a simple illustration. So what I just mentioned is that we can transfer inputs from local copies of a model to the black box model. And so this is also very useful in evaluating defenses. So there has been a lot of defense proposals that essentially try to make it difficult for the adversary to use gradients to inform their search for adversarial examples, because most attacks that compute adversarial examples rely on some gradients of the model to find efficiently perturbations that will force the model to misbehave. And so naturally you could think, well, what if I just remove these gradients, just hide the gradients, mask the gradients? And so this just makes the adversaries work a little bit harder, is that they need to recover these gradients. And so one very easy way to do this is to use a black box attack. So if you have a model whose gradients were masked, you can consider it as a black box and learn a copy of it. Because you learn the copy without the defense that masks the gradients, the copy of the model will have informative gradients. And then you can use this copy to find adversarial examples that transfer back to the model whose gradients were masked. And so what happens here, what you see here is the loss of the model whose gradients was masked. And so here, this is, in the origin, is an unmodified test input. So you can see it has very low loss. It's correctly classified by the model. And so if the adversary follows the gradients of the defended model whose gradients were masked and runs the attack on on this model, you can see that the loss does not increase that much. So basically, the adversary is unable to find an adversarial example because the gradient were amassed. So it appears like the defense is working. However, if instead the adversary follows the direction of indicated by the gradients of the local copy that I extracted by querying the model, basically you can see that the loss increases very sharply, very quickly. And so what this means here is that the gradients of the local copy are much more informative and allow the adversary to find adversarial examples that evade the model whose gradients were amassed. And so this is, in general, a very good test to run if you're designing defenses against adversarial examples, is to compare the performance of the model on white box attacks to the performance of the model on black box attacks. And if you see any differences, this indicates that the defense may not be working for the reasons that you expect. Any questions? Okay. So another principle is that requiring multiple parties to collaborate generally increases the security and the flexibility of a security mechanism. And we've seen instances of this specifically in privacy preserving machine learning with things like federated learning or ESA. So in federated learning, what happens is that rather than training the model centrally, you have a distributed set of users compute model updates locally on their individual training data sets. And then these users report the model updates, so the gradients, rather than sending their individual data back to the central party. So this is nice in the sense that the users don't have to trust the central party with their data. They just have to report the model updates. And so you can see how here we're separating the privilege, and this improves in some way the level of trust that is needed from users in order to have some form of privacy. Another example is ESA, where it's basically a framework to enable a central entity to analyze also data that was collected from a large set of users. And so the framework works in 3 steps. So first, the end users will encode their data as reports. So these reports contain their individual data points. And then they will send these reports to a shuffler. So the whole point of the shuffler is to break the linkability between the individual users and the data records. So this means after the shuffling operation, it's not possible for someone inspecting the reports to tell who they belong to. And then these reports are forwarded to the analyzer, which can do things like machine learning on these data points. And so here you can see how having a different party do the shuffling than the party that is analyzing the data can also improve the trust of users in this system. So this is, again, an instantiation of the separation of privilege. Yes?
So in federated learning, it seems like the gradients could still contain a lot of information.
Yeah. That's a very good point. So essentially what happens is that users are generally more comfortable with sharing model updates than the training data itself. But in order to have rigorous guarantees of privacy, you need to also noise the gradients that users report so that you don't learn anything sensitive from them. So if you combine federated learning with, for instance, differential privacy and like noisy stochastic gradient descent, then you can sort of achieve both forms of privacy, the one that is intuitive to users and the one that rigorously provides you guarantees that you're not memorizing any of the specific training points. And I'll come back to that later in a couple of slides. Any other questions? Okay. So the work factor principle basically looks at how much a defense increases the work that an adversary has to do compared to what the defender needs, what the overhead is for the defender. And so here I think it's interesting to look at attacks in the realm of poisoning. So if you look at things like watermarking and backdoor insertion, they're sort of the same type of attack, but with a slightly different scenario. So in watermarking, the defender is inserting poison points in its own training data to basically hardcode a specific output on these specific inputs, which helps the defender identify the model that it has created, so that basically you can prevent things like model theft. So if you eventually later want to figure out whether a specific model is the model that you created, you can present it with the specific triggers that you inserted, the specific watermarks that you inserted during training. And if the model responds with the output that you expected, you could assume that this is the model that you trained. Backdoors are essentially the same thing, but the attacker replaces the defender. So the attacker is the one inserting the poison and trying to make sure that the model will respond to this poison in a specific way that is of interest to the adversary. So here you can see how the only difference between these two things is that the attacker or the defender commits first. And based on the current state of affairs in this literature, it's basically easier for whoever is going second, because it's fairly possible to remove either the watermarks or the backdoors by doing things like compression or transferring knowledge to another model. And so here you can see how the work factor element plays into the machine learning security. If you instead take a slightly different angle at machine learning security, where machine learning is used to break security. So if you look at things like CAPTCHAs, you could think, well, now that we have very good vision models, why don't we use machine learning to solve the CAPTCHAs automatically? So people have tried to do this. And so it's natural to think, well, why don't we use adversarial examples as CAPTCHAs? This way, you cannot solve these CAPTCHAs with machine learning, because machine learning will misclassify the CAPTCHAs. And so here, it's not clear that this would be valuable, even if you were able to find adversarial examples that make good CAPTCHAs. Because of the low cost of human labor and things like human farms, where you can just submit CAPTCHAs and get them solved for a fairly low price, adversaries would just systematically try to evade the CAPTCHAs with machine learning, and if that fails, would just transfer it to human, and you would basically have gained very little security by doing this at the expense of trying to figure out how to use adversarial examples for doing CAPTCHAs. So here, it's another example why thinking about the work factor matters a lot. And so the last principle that I want to talk about is psychological acceptability. Here, the idea is very simple. We want to design security mechanisms that people will understand. People will understand why they're secure. Otherwise, they will not use them. And so I'm going to use this principle as an excuse to walk over a lot of work on privacy-preserving machine learning. And I'll start by introducing what I mean by privacy. So privacy is itself something very hard to define. And I think if we ask everyone in this room, probably most of us have different definitions of privacy. Fortunately, the research community has converged on a definition called differential privacy, which is both intuitive and comes with a rigorous formulation. So it allows us to also prove formally that we obtained this notion of privacy. And the idea is fairly simple here. If you look at this illustration, an algorithm is said to be differentially private if it's impossible for an adversary observing the outputs of this algorithm to distinguish whether the algorithm is operating in the first scenario here at the top or the second scenario. The only difference between these two scenarios is that in the first case, the data records corresponding to this individual were included in the data that the algorithm is analyzing. And in the second case, this same individual's training data was not included. And so what differential privacy means here is that it's impossible for the adversary to know whether this particular user existed or not. And so it's, in some way, it's impossible for the adversary to learn anything private about this user. And so you can state this formally by saying that the randomized algorithm M has to output, the probability that it outputs an output S has to be within a certain interval of the same algorithm outputting S on the second version of the dataset d prime. And so the size of the interval here is characterized by epsilon. And what this means is that the smaller the value of epsilon is, the stronger the privacy guarantee is, because the two cases are more indistinguishable statistically. So there are many ways to achieve differentially private machine learning. And perhaps the most naive way would be to basically noise the output of machine learning, which is the model parameters. So you could think, if I want to provide privacy, I will just noise the model's parameters, and this will break sort of the sensitive information that was included in them. Unfortunately, it's very hard to analyze the sensitivity of these parameters to the training data, to the individual training records, after the model has trained. So in practice, to provide privacy in machine learning, we perform the randomization during training. So we add noise during the training because it's easier to identify how sensitive the model updates are to specific training points. And so what we have to do is basically make two small modifications to stochastic gradient descent in order to obtain models that are differentially private. The first modification is that we clip the model updates. So we clip the gradients that we compute during training, and this allows us to basically bound the sensitivity of these model updates to individual training records included in the data. Once we've done that, we basically add noise, so random noise, to the model updates before we apply them. And so this gives us the randomness that is needed to protect the privacy. And so this is essentially the only two changes that we have to make to stochastic gradient descent. And so if we train the model with a good estimate of the sensitivity and sufficiently enough noise, then we'll get a differentially private machine learning model. And so in practice, this is very easy to do. We even recently put out an open source library, TensorFlow/privacy, which allows users to basically wrap existing optimizers into differentially private variants. And so it literally takes 2 lines to go from a normal stochastic gradient descent to a differentially private one. However, it's still fairly hard for the end user to understand why this whole procedure here provides privacy. Even if you explain this to a non-technical person, they will most likely not understand why it is the case that the individual training records that they will provide you will not be reflected in the final model. And so this is a very common problem in using differential privacy, is that it really has this deployment limitation due to the fact that it's hard to explain where the guarantees come from. And so in our group, we basically started working for that very reason on another approach to provide privacy during learning, with psychological acceptability being one of the core requirements from the design phase. So this approach is called PATE, which stands for Private Aggregation of Teacher Ensembles. And so really from the start, the idea there was we're going to design the approach to be easily understood by humans, even though that they're not familiar with the concepts of differential privacy. And so the idea is that we start with the sensitive training set on the left, and we're going to partition it in n subsets of data. The only requirement is that one subset of one individual training record should only be included in one of the subsets of data. So these are real partitions. And using these n partitions, we're going to train n teacher models. And so here, there are no requirements on how we train these models. They could be decision trees, they could be logistic regression, neural networks, and they don't have to be trained with any form of privacy. So here, what we have at this point is an ensemble of n models that were each trained independently on a different subset of the training data that is sensitive. So the question is, how can we deploy this ensemble of models to make privacy-preserving predictions? And the answer is that we're going to aggregate their predictions rather than revealing the individual votes that each teacher is making. So the naive way to go about this would be to take the histogram of votes and to output the class that received the most votes. So whichever class was most often predicted by the teachers. This would provide a form of privacy if all of the teachers agree. Because if your training record was included in the data, it's only included in one of the partitions, so it only influenced one of the teachers. So if all of the teachers agree on the prediction that they're making, then it means it's a generalization. It's not a fact that depended on your specific training point. However, there are corner cases that would violate privacy. So in cases, for instance, where you have two classes that have about the same number of votes, you can see how changing one individual training record would change, in the worst case, the predictions of one model. And so that could result in the classes that were running up, they would basically swap. So you would have, instead of predicting one class, you would predict the other because it just got plus and minus one vote for each of these classes. And so in these cases, the output of the aggregation could depend on a specific training record. And so this is why we have to add one more step into our approach, which is to add noise to the histogram of votes before we output the noisy argmax. And so this allows us to basically take into account these corner cases, because we'll basically just output something random in these cases, just one or the other class randomly. And so if we look at this approach here, all the way to here, we have essentially something that can provide us with predictions that are differentially private. So we can submit inputs to the aggregated mechanism, and it will respond with a differentially private label. And so it's easy for us to explain to end users why their privacy is protected using this approach, because we can, again, go over the voting mechanism. There is one final catch, is that every time we make a query to this aggregated mechanism, we have to pay a little bit of privacy. So our privacy budget increases every time we make a query. And so we have one last step where we take the predictions of this ensemble and use them to label a set of public data that is originally unlabeled, but that we label with privacy. And this allows us to transfer the knowledge from the ensemble to a student model in a privacy-preserving way. And then at test time, when we want to deploy this, we can just erase all of this and keep the student as the only model that will respond to user queries. And we can respond to as many user queries as we want. The privacy budget will be fixed, and so we'll have the same strength of privacy guarantees throughout the use of the model. Yes?
For the public data, can it be the same ones that the teachers have seen before, or does it have to be completely?
It has to be different. Basically, the public data should not contain sensitive information, because you will not protect it. You will label it with privacy, but the inputs themselves should be public. So this is an assumption that you make, which the previous approach, the noisy stochastic gradient descent, did not make. So this is sort of the price that you pay for the flexibility and the easiness of explaining where the privacy guarantees come from. Yes?
If you have access to public data, why do you need to train the teacher models at all?
Right. So usually it's easy to have access to public data that is unlabeled, but having quality labeled data is usually much harder. And so that's sort of the use case that we're going for here. OK. So this concludes sort of the overview that I wanted to make of the principles. Again, there are more principles, but I don't want to cover all of them in the lecture. I'll let you look at the report if you're interested. And basically, by doing this work, it occurred to me that there are a few directions that we haven't explored much as a community. And I think they would have a lot of value if we made progress in these directions. And the first one that I want to discuss is model assurance and admission control. So let me provide a little bit of motivation and explain what I mean by this. If you look at machine learning, so far we've mostly been looking at average case performance. So we're tracking metrics like accuracy, which essentially is accounts to doing testing. And in security, we often care about the worst case performance of the system. So we want to do something that is not testing, but that is closer to verification. And so ideally, we'd like to move from this testing to verification in order to have better security guarantees for our systems. And in cases where we have made a lot of progress, like privacy-preserving machine learning, we can see that this is already happening. So we have ways to measure, to test privacy-preserving models. So for instance, we can insert secrets in their training data and then observe the privacy-preserving models to see if we can recover these secrets. And so we came up in our group with some metrics like exposure, which are basically just measuring how much information the privacy-preserving model will tell us about the secrets that we inserted in its training data. And so this amounts to testing whether the privacy-preserving model memorizes the training data that it's analyzing. And this is testing. This does not provide worst-case guarantees. It's just testing. But we can also analyze the privacy guarantees in the worst case of these models by doing something like differential privacy. So in privacy, we've made a lot of progress. We're able to do both testing and verification. But in general security for machine learning, this is not the case yet. And so I'm arguing that we should work on two things. At training time, we should establish with confidence that the system matches a set of security requirements. And I'll come back to what I mean by these requirements. And this amounts to what is typically called model assurance in computer security. And at test time, we have to, given an input, validate whether we'd like to make the prediction on this input. So given an input and the output of the model, decide whether we want to admit this input-output pair into our pool of answers. And so this is more like admission control. And so a preliminary requirement to being able to do this is that we have to specify what we mean by security and privacy. And so informally, it's easy to define what we mean by security. We want the learning system to behave like we intended it to behave. So we want it to model the task correctly. So that could mean that the implementation is correct. You don't want things like numerical instabilities. That could mean that the machine learning model should solve the task. So you want correct predictions. You want integrity. And that could also mean that the model only solves the task that you intended and not additional tasks. So you don't want things like poisoning, like backdoors, as I just discussed. However, it's still an open problem how we can specify this formally with precise semantics and without ambiguity. So if more people work on this particular question, this will have a lot of implications because that means we can ground the efforts that we're making and have more principled approaches to security and machine learning. The good news is that we have instances where we have successfully defined this policy. So in the case of privacy, we have the intuitive notion of privacy that we'd like. We don't want the model to reflect any of the sensitive information that it's analyzing. And we also have the formal specification that corresponds to that, which is basically differential privacy. And so again, that's why I'm pushing differential privacy as a great example and an inspiration of what we should be doing in security as well. And beyond the advantages that I already mentioned, which is that it's both intuitive and rigorous, it also makes very little assumptions about the adversary's capabilities, knowledge, and goals. So this is a major difference compared to the previous definitions of privacy that existed. So if you look at things like k-anonymity, they eventually were weakened by the fact that if the adversary has access to auxiliary information, it can combine the auxiliary information and what it's learning from the system that you're trying to protect to break the privacy. And this is not possible in differential privacy because the definition makes no assumptions about what the adversary already knows before it starts interacting with your system. One other very big advantage of differential privacy, at least in my opinion, is that it aligns the goals of privacy very well with the goals of machine learning. So in privacy, what you want is to avoid basically overfitting to specific training points that are included in the data. And this is something that will directly help with generalization. It is one of the goals of machine learning. And what's very nice is that we've observed this synergy in practice in mechanisms that we designed. So for instance, in Pate, we were able to improve simultaneously the utility and the privacy of the mechanism by observing that privacy and utility were in fact cooperating. So let me give you a very concrete example. If you remember, we have this voting mechanism where we aggregate the votes of the individual teachers. And what we realized is that if we explicitly check for a large consensus among the teachers before doing this aggregation, then we can improve the accuracy and the privacy of our system. The reason is that if almost all of the teachers agree, so if there is a large consensus, then the prediction is more likely to be correct because it was made independently from a lot of subsets of the data. And it's also more private because the probability that changing one training record would change the output of the aggregation is very low. And so you have very strong privacy when you have a very large consensus. It's hard for the output of the mechanism to depend on a specific training record. And so by adding one small step before the aggregation that basically checks whether there is sufficiently enough consensus before proceeding with the noisy aggregation, we were able to increase simultaneously the privacy and the accuracy of the system. So this was really a very interesting observation, and it really motivated me into working more on this aspect of privacy in machine learning. So assuming that we came up with a security policy for machine learning systems, there are still many things that we need to figure out. One example is how do we measure coverage, right? So when we do verification in traditional security, we have to figure out how much of the logic of the system we've exercised so far. And typically we use something like line coverage, which will not correspond to anything in machine learning, because if you run a machine learning program, typically if you make one prediction, it will execute all of the lines of the program. So the line coverage doesn't tell you how much you've exercised the logic of the machine learning model. So there are many candidates. People have looked at neural coverage, which basically looks at the number of neurons that you've activated. But then progress was made, and people have looked at things like the distance between activation vectors. And you could imagine maybe that you could use capsules activity vectors, and so on. So it's not clear yet what the right granularity is for expressing how much of the logic you've exercised so far. Yes?
So how would you know whether a metric was good or not? Like in the code case,
Mm-hmm.
we can at least like say whether line coverage tends to correlate with having found all the bugs.
Mm-hmm.
So there's like a kind of final metric of truth, but what would that be in the ML setting?
That's a very good question. So this part of the presentation is more of open problems than solved problems. So I'm really trying to bring up points that I think deserve more attention. But it's true. It's really not clear how you would evaluate whether you've came up with the right metric. And this was actually part of the questions that I had below, which is like how do you, a lot of these heuristics need to be bootstrapped. So you don't know what is the right set of inputs to bootstrap the heuristic. That's also another good question. And basically what you were saying is how do we define the set of valid inputs to the system so that we can know whether we've measured all of it and we have full coverage. So yeah, so these are all open questions. So let's now assume that we've solved assurance at training time. We still have the test phase of the system. And there, what I was arguing is that we're basically deploying machine learning in settings where we have very weak authentication. So this is very similar to search engines, which also have very weak authentication. And so we really need to be able to come up with sandboxing techniques where we can run the model on the candidate input and decide whether we want to release the output of the model, and so whether we accept this input-output pair as part of our pool of answers. And this is really difficult because when we're using machine learning, it generally means we don't know the underlying distribution. So knowing whether this input-output pair should be a valid one or not is very difficult. And so there are many ways that you can go around this. People have looked at things like Bayesian deep learning to estimate the uncertainty in the predictions. I'll just walk over an approach that I've worked on myself with others, which tries to estimate the support for a specific prediction in the training data that the model has analyzed. So the idea is basically that you break up the neural net and you look at each intermediate representation, so each layer's activation, and then you perform a nearest neighbor search in this representation space to look for the training points that have the closest representation to the test input that you're processing at the moment. And so if you look at the labels of these training points that have the closest representations, if they all agree with the prediction that you will eventually make at the output of your model, then this tells you that in some form you have support in this prediction in your training data. So you have support points in the training data for making that specific prediction. And so if you look at, you can calibrate this mechanism to basically estimate how much you expect the training labels to agree with the predictions. And so this allows you to calibrate the uncertainty estimate. You can also basically modify the representations themselves to better support the search. So this is something that we worked on very recently, and the work should appear soon online. The idea basically is that we add a penalty to the training loss that encourages the representations from different classes to be closer together. So we're basically encouraging different classes to be more entangled. And so this may seem a little bit counterintuitive because you might want, at least at first, if you think about it only very quickly, you may want to increase the margin between the different classes to better separate the classes. But what we found is that the opposite is very beneficial in the internal representations. So if we entangle different classes and bring their representations closer together, we find that the representations form basically clusters that are semantically coherent and that are less based on the labeling information and more on the semantics. And so if you think about it, this makes sense because the model basically is incentivized to take points from different classes and project them very close in the representation space when it makes sense, because these points from different classes may share semantics. And so because you still have the cross-entropy term in your loss, you will still separate the classes eventually in the last representation space that you learn. But what we found is basically by having this penalty, so we call this the soft nearest neighbor loss, we're basically able to modify the representations in a way that the nearest neighbor search provides better results. And so when we run things like the deep K nearest neighbors, we have better calibrated estimates of the uncertainty of the system on these representations. Because basically the representations project the outlier data more consistently away from the expected training manifold. Okay. So this concludes this part of the presentation, and if I still have a few minutes, like-ish, a very few minutes. So the last thing I want to argue is that in cases where model assurance fails, it will also be very useful to have auditing. So very quickly, what I mean by auditing is that we need to figure out first what information we should collect and how to analyze it. And this will be helpful to basically identify threats reactively, but also proactively. And it will also increase the psychological acceptability of security mechanisms that we put together. So let me give you a few quick examples. So in privacy, in the approach that I presented, you can see how logging the individual teacher votes is a good way to audit how the privacy-preserving mechanism is working, right? So if you log the different teacher votes, and this is actually what we do in practice, we can then send them to something called the moments accountant that will take these votes and estimate the different probabilities that are required for us to compute the privacy guarantee. And this not only enables us to compute the privacy guarantee, but also enables us to understand which parts of the mechanism contribute the most to the privacy budget that we have to expend. And so this, in turn, informs the design of the approach, because it tells us where we have the most room for improvement. A second example that I wanted to give is when we look at how the models perform with privacy, to learn things about the data and to explain why privacy-preserving models may not be able to perform as well as non-private models. So this is a very simple technique that we put together where we rank the training data. So the first way that we rank the training data is by how much noise we can insert during learning before we start not being able to correctly classify this training point. So if a training point is very robust to noisy gradient descent, it will be ranked higher. If as soon as we insert a little bit of noise, we're unable to correctly classify this training point, then it will be ranked lower. And then we compute a second ranking of the data based on how far the training point is to the decision boundary. So this can be estimated with things like adversarial examples. And so the further the point is from the decision boundary, the higher it is ranked, and the closer it is, the lower it is ranked. And if we look at the intersection of these rankings, and when they disagree, we can essentially find submodes of the training data that are points and small clusters of points which have very few points in them. So these are very small clusters. And so what happens is that the privacy-preserving machine learning model has to memorize these training points in order to be able to correctly classify. And so if we compare the privacy-preserving model to a non-private model, it will have lower test accuracy because it was not able to learn these clusters. And so at test time, when we present a few test points in these clusters, it won't be able to provide the right answer. And the non-private model was able to provide the right answer because it just memorized these few examples. And so this is just an illustration of how, by auditing the learning and trying to interpret why the model is failing in some way, we can then come back to the end user and explain, well, we have a privacy-preserving model. It does have lower accuracy on paper than your non-private model. But maybe this is something that you should accept, and maybe this is actually a desirable property of the privacy-preserving model, because if it had the same level of accuracy, it would basically violate the privacy of your training points. Okay, and so moving forward, this is really the conclusion slides. So I said it many times, we really need to spend a lot of time specifying security and privacy policies. It's really unclear at this point what the right abstraction is to have precise definitions and very little ambiguity. We also need to think about what is the trusted computing base. So we have usually thought about the machine learning model in isolation, but it's deployed in a much larger pipeline. There is the feature extraction. There's the process that goes after the model makes predictions to make decisions based on these predictions. There's the hardware, the software stack. So unfortunately, I don't have time to talk about this. The second thing is we need to work on admission control and auditing in cases where we're unable to have assurance that these security policies are met. So things like sandboxing, input-output validation, compromise recording, they will help with security and with practical security. And finally, I encourage you when you're working on these problems to think about how you can align the goals of security and privacy with the very goals of machine learning. So if you look at things like differentially private machine learning, this is most likely one of the reasons why it's so successful. It's because it really goes well in hand with machine learning, and in some ways you can think of it as a regularizer. And so this really helps pushing forward the adoption of these techniques in practice in the real world. With this, I will answer any questions you may have. I'll just point out that we have 2 open source libraries that you can play with. CleverHans is more related to security. TensorFlow/privacy is about privacy. The technical report that has everything that I talked about today is up there. And the blog is more informal posts about these general topics. So with this, thank you for your attention.
So we'll now have 15 minutes for sort of open discussion. So if you have questions about the talk, you should feel free to ask that. This is also a good time to bring up any of the discussion questions you submitted on Piazza as well.
And I'll be around for like 40 minutes-ish, so I'm happy to go over time. Yeah.
You mentioned, I guess you mentioned a little bit near the end about privacy-aware learning helping generalization. What I was familiar with was that, for example, adversarial trained models were usually doing worse, on the target test set, sort of like as a reduced overfitting kind of thing. Can you, I guess, talk a little bit more about, I guess, and specifically, like, for example, in the soft nearest neighbor loss example, like how that improved performance? I think you said it improved performance?
So the soft nearest neighbor loss, it basically has no impact on performance. Like if you look at the test performance, it has very slight variations. Usually it improves, but not in a significant manner. What it improves is the similarity structure of the representations. So how different points are projected. It doesn't, we're not claiming that it will improve the final performance of your model, the accuracy of the predictions. It basically improves the structure of the representations in the way that it projects the outlier data in a way that makes it easier to identify it as being outliers by looking at the neighboring training points in the representations.
And this isn't overcome like by a adversarial, like this implies robustness to adversarial examples, for example?
No, so like if you have access to the representations themselves, you could still find adversarial examples for it. What we're basically showing is that it improves how you measure uncertainty on these models using this specific approach based on the nearest neighbors. But if you had like white box access to the model and you attack the neural network directly, then you could still force it to make a mistake. So there's a difference between the neural network making a mistake and you being able to tell that the prediction that it's making has very low confidence, so that you don't use this prediction and you just reject the input.
I mean, I see what you're saying about needing the ability to understand sort of what's happening inside the layers.
Yep.
Do you think there should be any actual laws put into place regarding machine learning privacy, and what would the ramifications of that be?
Is this talk recorded?
Yes.
Can we talk about it offline?
Sure.
Yeah. Sorry. Any other questions?
So on this sort of model, well, I guess you had a few different things on auditing, but one was this analogy to code coverage, where we kind of want to test all of the paths. I guess one thing that made me think of is these issues in adversarial examples like gradient masking and other things, where basically a model seems secure, but then on further testing, turns out to not be secure. So I guess it seems like it would be quite interesting if there was a way to have a notion of sort of how well
how much
had been in these sorts of scenarios.
Yeah, and I guess that's what. So like coverage is not perfect because you're also measuring coverage, and if you're going to be testing, you're going to be testing for specific things, and so that's going to be different from doing verification. But it's true that it would be very helpful to have a good idea of how much of the input domain you've covered by the testing. And even in things where you have like certifiable robustness, where you're saying I'm going to be robust within a certain epsilon ball of the training points, it would be useful to know whether the training points cover enough of the input domain that you're confident in deploying the model on a specific task or in a specific scenario. But I'm not sure I have an answer to how we would measure this coverage. And I think you raised a very good question, which is how we also compare different metrics, where it's clear that measuring coverage through neural, the fraction of neurons that you've activated probably doesn't reflect the logic that you've exercised that much, because I can think of many corner cases where you would just exercise a few neurons and that would be enough. Activations do provide in some way a more natural way to measure coverage, because you're looking at the granularity of the layers, but even that is not clear. Like if you have a ResNet, should you look at the blocks? Should you look at the individual layers in the blocks? Yeah. So I think it's a pretty open area, and I'm not aware of that much work that looks at things like auditing or like even model assurance beyond the certifiable robustness line of work.
Yeah, I guess, well, the closest thing that it reminds me of is interpretability, maybe, which
that's
can be thought of as a way of auditing.
Yes, definitely. I think it can be seen as a way of auditing. But yeah, there's not that much work in like the context of security. And I think it would be very useful, just even, yeah, interpretably is a good point, because it goes very well in hand with psychological acceptability, and we want to be able to explain just the failures of the model, even if that's reactive. That would be already a better state of the art than what we have right now, where we're presented with failure and all we can say is, oh, the gradients were informative. So it would be good already to have much more auditing, even if it's not proactive. Ideally, it would be proactive, where you could say, oh, this looks suspicious. We should look into it more and come up with specific defenses for this new threat. But already being able to explain the failures would be a good start. Yes?
So in the auditing section, when you were talking about how there are certain, you perform two rankings of the training points based on
Yes.
the robustness to noise versus how certain the model was in classifying that particular training point, and you said that pretty much we had to kind of give up those points because it would no longer be a differentially private model, because the regular model that was non-private was just memorized.
Right.
Is there any better way that you would kind of not have to sacrifice just classifying all those points, and you'd still maintain some semblance of that?
Yeah, I think that's a very good point. Like, I could see how you would do things like active learning, or basically you know that these clusters are not sufficiently well represented in the training data. So now you could go and collect more data that has sort of the same semantics, and then include it in the training set to sort of increase the size of these clusters and make it possible to learn with privacy. So that would be a very simple way to deal with that. I think, yeah, in general, this is also another direction that we haven't explored that much, and it could be also applicable to security. For instance, like if you have good estimates of uncertainty, then you can, when you receive a test point for which you have very low uncertainty, you can sort of flag it as an area of the input domain where you don't have enough support. And then you can go and collect more data and update your model. And hopefully it would increase the uncertainty for this particular part of the input domain. And if you do this gradually, that might make your model just have more coverage of the distribution that you're interested in classifying. Obviously, this also allows the adversary to manipulate sort of where you're going to sample more training data. So you could see the adversary would submit test points just so that you query specific parts of the input domain. So I could see how this would be gamed as well. But it's a possibility that I'm not aware of any work that has considered this, but I could see how it would be useful.
follow up on the question I asked a few minutes ago about the deep nearest neighbors.
Mm-hmm.
You said that you said, okay, well, if we have, sure, if there's a white box attack and they, have access to the layers, they can still create an adversarial example.
Mm-hmm.
But you also mentioned, and it's sort of known that, a black box attack can, still like recreate, still do pretty well. So I guess, does that, so is someone able to, is this kind of sort of model, is training with this sort of, loss to, create these informative clusters? It's not any, I guess it's not any more resistant to, sort of like coming up with, bypassing, I guess, this, like what you're saying, like probing the input space,
Mm-hmm.
Just getting access to predictions,
Mm-hmm.
As well as, if the attacker knew a priori that it was trained with this method, that they could, recreate a model that, has different weights but performs similarly and then run attacks on that. Is that the case? Did you examine that in that work?
Yeah, so what we found, so it was actually quite interesting. So what we found is that if you, as the adversary, it's not a good strategy to use the soft nearest neighbor loss in your model because it introduces a lot of variance in the way that the gradients are in the resulting model, and so it makes for a very poor transferable adversarial example. So if you take from a model that was trained with soft nearest neighbor loss to another model that was trained with the soft nearest neighbor loss, they usually don't transfer very well. So we found it's more, it's a better strategy for the adversary to take a vanilla neural net that was not trained with the soft nearest neighbor loss to attack a model with the soft nearest neighbor. And so that's what we did in our experiments.
That's very interesting.
Yeah, and so basically, coming back to your question, yeah, the reason that we're doing this is really to improve the support to measure uncertainty. We're not saying that the model itself is more robust. We just want to improve the way that we project the outlier data and then measure its uncertainty with the nearest neighbors.
For sure.
And so that we also measure that on things that are just like different test distributions that are not adversarial examples, just like you train on, I don't know, SVHN and test on CFAR. And how, like if you do that with normal softmax, the softmax will still output fairly large confidence on the other distribution. And so here we show that it has much lower confidence. It can identify that this is not the test distribution that was intended.
Okay, that last part is pretty cool.
Yeah, I mean, I think it will help a lot to have uncertainty estimates that are reliable, because basically, even if we have a perfect machine learning model, we're deploying it on inputs that are not validated. So we need to be able to know where the limits of the model are, and this will have like an impact even in cases where we don't have adversaries. So if you have a driverless car, it would be very useful to know in cases where it has low certainty. You don't want to leverage the model as much. If you're making medical predictions, then you want to be able to convey to the doctors using the machine learning models that you have very low confidence on this particular patient. So in many cases, it will help to have better uncertainty estimates. So that would definitely be another direction that I would encourage everyone to work on.
Time for one more question. Has something they'd like to add?
I'm not really familiar with like traditional computer security, so could you like go over like some similarities between that and what you discussed today?
So what in particular, so you just want to know like examples of how traditional computer security is similar to what I discussed? Well, I guess like it's very, like there are a lot of techniques for doing things like verification. So I guess like one comparison point I had was with like line coverage. where you want to find an analog in machine learning where you're able to measure how much of the logic you've exercised. So in traditional computer security, when you verify programs, that's one metric that you can use, is how much of the logic of the program you've exercised. I guess my talk is arguing that machine learning security could be approached in a different way than traditional computer security. So, but of course there are things that are similar. So I guess another example is like what I discussed about auditing, for instance. If you look at things like search engines or spam detection, there is also very weak authentication in these traditional systems. And so that calls for auditing. And so auditing has been very helpful in improving the security of these systems. And so I can see how if you have a machine learning model that is deployed, let's say, behind a prediction API, then you have the same level of concern where you have pretty weak authentication when you receive queries that your model has to classify. And so in these cases, that's why I would say that auditing should be also useful in the case of machine learning. So these are just examples. I'm not sure we have time to go over the whole computer security field.
Yeah, so we should end here since it's 5:30. But let's all thank Nicola again.
Thank you.
If anyone had additional questions,
Yeah,
you'll be around a bit longer.
Yeah,
so,
yeah.